friends. So today we are going to learn about depth first search coding pattern, and in my opinion this has to be one of the most popular coding pattern out there because this coding pattern solves some of the real life problems that many companies or many entire products that are completely built upon, and that is why interviewers love asking this problem. So if you want to ace any technical interview, you are guaranteed to be asked a problem that can be solved using depth first search at one point or the other. And that is why I am asking you to pay extra attention to this problem. The flow of this video is going to be such as that first I am going to talk about the overview of what breadth first search problem is, and in the overview I am going to explain that what type of data structures are being used to solve this problem and how each data structure uses depth first search. Second thing I'm going to talk about it, what is the typical workflow that looks like for a depth first search kind of a problem, and in the end I'm going to show you three different real life LeetCode problems that has been really popular problems and that has been asked in bunch of different big and small companies all across world. So please, I urge you to pay extra attention because this video is going to be full of so much information that you only need to learn once and then you would be able to use it forever in your interviews. Let's understand that what does a depth first search is. Depth first search is basically a traversal mechanism. And where does it traverse over? It traverses over trees and graphs. So basically this is depth first search is simple technique to iterate over any given tree or any given graph, and this traversal techniques allows you to solve some of the most popular real life problems such as like going through a maze or solving like a snakes and ladder problem, or problems such as building path between any two endpoints and bunch of different ideas. So first let's see that how does DFS is being applied on a tree, and then we will see how it applies on a graph, and then we will try to see that what does a typical workflow looks like. Now you already know that how does a breadth first search works. Breadth first search is typically a notion where we move out in the breadth before moving out in the next iteration. That is exactly the opposite of what depth first search is. And in the DFS we go or we pick a branch, we iterate all the possibilities of that branch while keeping track of the nodes that we have iterated over, and when we run out of all the possibilities we are going to do a backtrack and see if there are any more possible ways where we can iterate over. If there are no possible ways exist, we are going to backtrack again and then move on to the next values in that particular subsequent branch before backtracking to the previous root node again and iterating the same process for the remaining portion of the tree. So that is exactly what we are doing here, where you see that first we iterated in the depth in the left side of the subtree. So we iterated through all of this path, then we ran out of all the possibilities because there were no children of this node, so we backtracked. There were no nodes that we forgot to cover. Again we backtracked, we covered this portion. Again, after existing all the possibilities, we again did a backtrack and moved on the right side of the subtree and keep on repeating the same process until we run out of all the nodes, and eventually we would backtrack and come back to the root node. And this is how DFS typically works in a tree. Now for a tree there are three main methods, and that is Inorder, preorder and postorder, that I'm going to talk about next in this video. But this was a general idea or the broader pictorial representation of how a depth first search works in a tree. Let's see how it works in a graph. So this is just a random graph I draw, and even in the graph we can start from any point. So typically in a tree we will usually start from the root node, but that is not the case in the graph. We can start from here or we can start from here or any other node. So say for example we start from this node and we go in one direction. So suppose we pick this neighbor, then again we are going to keep track of all the neighbors that we are visiting, and we are keep going until we run out of all the neighbors that we exist in that path. Once we run out of all the neighbors, we will do the backtrack, keep coming back, and then eventually we will come back to the same position where we started. Now again we check that have we existed all the possibilities, and the answer is no, because we still have nodes on this path that we haven't visited. So again we will go in depth first search manner, which means we are going in depth to that path as well, and then Again, after existing all the possibilities, we will do a backtrack, come back to the neighbor or the root node where we started in the graph, and this would be a typical depth first search flow in any given graph. So after seeing these two things, first question should come to your mind is that why depth first search is different for tree and graph. Why in the tree I mentioned that there are three different ways to iterate over. There is in order traversal, there is pre-order traversal, and there is post-order traversal. Meanwhile, in the graph, we don't have to worry about any such items. But in the graph, we have to worry about something else, and that is called loops, which is not the concern in a tree. So I'm going to explain both of these things right now. So first, let's see that what does an in-order traversal, pre-order traversal, and post-order traversal looks like for a tree. Again, for the simplicity, I have already drawn an example, and let's see every single traversal one by one. So first, we are going to start with a pre-order traversal. Now, what does a pre-order traversal means? Now, first understand that from any given place, we have two possibilities. First possibility is we go either left side or left subtree. Second possibility is either we go on the right subtree. And there is a possibility that when we are going to do some process on the node currently we are at. And that is what this pre-order, in-order, and post-order, all of these three techniques do. That it allows us to determine that when we are going to process the node we are currently at. So in the pre-order traversal, we are going to process the node first. In the in-order traversal, first we are going to go in the left, then we are going to process the node, and then we will go in the right. In the post-order traversal, first we will go on the left, then we will go on the right, and in the end, we are going to process the node we are currently at. So this is what all of these three techniques refer. So first, let's see the pre-order traversal in action. So in the pre-order traversal, the flow is going to look like this. That first we are going to visit the node. So first thing is going to be the node. Then we are going to visit its left subtree, and then we are going to visit its right subtree. So the flow is going to look like this. That we are going to start from the root node because that's a given fact. We are going to visit the node. So first item we are going to do any action is going to be on the node number 5. Then we are going to visit the left subtree if there exists. And left subtree exists. So again, this is the entire left subtree. Again, even for the left subtree, we are going to repeat the same process. And the process is that again, we are going to visit the node first before visiting its left subtree and the right subtree. So again, the left subtree, currently the next node we are going to visit is going to be the node number 2. Again, for its entire left subtree, it only has one node. So again, we are going to visit node number 1 after that. After visiting node number 1, we are going to do the backtrack. And then for this node number 2 that we have already visited, we haven't visited its entire right subtree. So that we are going to do next. And the next node we would visit is going to be the node number 3. Now what happened is that now after this 4 iterations happen, we have taken care of the entire left subtree from the root, and we already took care of the root node. That was node number 5. So now we are going to take care of the entire right subtree. Again, even for the right subtree, we are again going to apply the logic of node, left, and right. So again, this is the node. Currently, it does not have anything in the left, but we are going to visit node number 6 first. It does not have anything in the left, so we are going to move in the right. Again, for the right subtree, it has these two elements. So first, we are going to take care of value number 8 because node, left, and right. And after that, in the end, for this node, we have the node number 7 that we have to take care of. So in the end, the last node we are going to visit is going to be the node number 7. So if we want to see the full traversal is going to look like this. And this is how we are going to move in the pre-order traversal fashion. Now let's see that what would be the in-order traversal looks like. Let me clean this up a bit. So for the in-order traversal, there is a slight difference. And the difference is first we are going to iterate the entire left subtree. Then we are going to visit the node, and then we are going to visit the entire right subtree. And we are going to recursively or iteratively keep on repeating the same thing for the entirety of the tree. So we are again going to start traversal from our root, but we will have to visit the entire left subtree before visiting the root node. So in the entire left subtree is going to be this one. But even for this entire left subtree, the same properties applies again. And again, even for this 2, we will have to visit the entire left subtree, and that is going to be the value number 1 only, because 1 does not have any more children. So the first node we are going to visit is going to be the node number 1, and then the next node we are going to visit is that we are going to do a backtrack. And since for this 2 we have visited the entire left subtree, so then we will visit node number 2. And then even for node number 2, we still have elements in the right side of the subtree that we haven't visited. So we are going to do that. The entire right subtree is only comprised of value number 3. So again, we are going to visit node number 3 next, and then we can backtrack. Backtracking from 2, now we have taken care of this entire portion, so we are not worried and we can go back. Now at node number 5, we can say that we have taken care of the entire left subtree for the node number 5. So it is safe to visit node number 5 next. We will visit node number 5. Then again, we are going to repeat the same thing. Now, even for the node number 5, it still has element on the right side of the subtree that we haven't visited. So we are going to repeat the left node right technique again for the entirety of the right subtree for this portion. So for this portion, since for node number 6, it does not have anything in the left side of the portion, we are going to visit the nodes. We are going to visit node number 6. Then again, for these two portions that is present in the right side of the subtree, we are going to repeat the same thing. So before visiting node number 8, since node number 8 has a value number 7 in the left side of the node, we are going to visit node number 7 first before visiting node number 8 in the end. And then we would have taken care of, or we would have visited all the nodes in the Inorder traversal. Now, seeing from the solution that we have visited, you should be able to infer a very clear thing right now. And this is actually a solution of a very popular real life problem. You see that all of these values, they are actually presented in a sorted array. And why they are presented in a sorted array? Because the tree that I draw over here was actually a binary search tree where I'm maintaining a property that every element on the left side of the subtree is going to be less than the root node, and every element on the right side of the subtree is going to be the greater than the root node. And this is present for every single node that has a left element and the right element, that all the values on the left are going to be smaller than the root node, and all the values on the right are going to be greater than the root node. And this is how a binary search tree is defined. And using Inorder traversal on a binary search tree, we are actually able to generate the sorted array. And see, you just solved a very popular coding problem that is being asked in a bunch of companies. I'm actually going to show you the LeetCode proof that this question exists, and you already know how to solve it. All you need to do is do Inorder traversal on a binary search tree to find the sorted result. But now let's just go back to our technique. And now let's see that what does the post-order traversal mean. And let me again clean everything up, and I'll show you the post-order traversal as well. Now in the post-order traversal, first we are going to visit the entire left subtree for any root node. Then we are going to visit entire right subtree, and in the end we are going to visit the node. So for the 5, what we are going to do is first we are going to visit entire thing on the left subtree. Then we will visit everything in the right subtree. Then in the end we will visit this node number 5, and we are going to iteratively or recursively keep on repeating the same process. So first let's see what would happen for this node number 5. We start at 5. It has elements on the left subtree that we haven't visited, so we go on the left subtree. Again, even for this 2, it has elements on the left subtree that we haven't visited, and that is value number 1. Now for this value number 1, it does not have any more left or right children, which means we are sufficiently able to visit this node. So first node we are going to visit is going to be node number 1. Then we are going to backtrack to its previous node, that was going to be node number 2. Again, even before visiting node number 2, we will have to visit the entire right subtree for that node. So we are just going to do that, and that is going to be node number 3. So then we are going, after visiting node 1 and node 3, we would be able to visit node number 2. After visiting node 2, we will again backtrack to node number 5, stating that now for this node number 5, the entire left subtree has been taken care of, but it still has elements on the right subtree that we haven't taken care of, that we are going to work upon right now. So even for the right subtree, we are going to apply the same logic. So for this node number 6, since it does not has any nodes on the left, it still has nodes on the right that we haven't taken care of. So again, we are going to visit the right subtree for node number 6. So that is going to be node number 8. even for node number 8, it still has elements on the left that we haven't taken care of, that is node number 7. So next value after visiting this node number 2 is going to be node number 7. After 7 we are going to visit node number 8. After visiting node number 8 we are going to go backtrack and visit node number 6, and in the end we are going to visit node number 5. So what we did in this post order traversal is that we took care of all the elements that were present at the leaf before moving back to its like predecessor, and this would be the post order traversal for this tree. Now after learning in order, pre-order and post order traversal, the first question that should click your mind is that why this is only limited for trees. Meanwhile, the DFS method that you already know can be applied to trees and also graphs. Then why it is only limited to trees, where we need to do like this in order, pre-order and post order traversal, meanwhile nothing for the graphs? And the reason is quite simple. The reason is that for a graph we are actually able to start at any single position and start iterating in the DFS fashion. Meanwhile, for a tree, we are limited to start at the beginning. And when we start at the beginning, we have couple of possible ways to iterate over that. Either we are keep on going into the left direction before moving on to the right direction, or we are going to mark the node first before moving the nodes again. And that is why this in, pre and post method is in action and for the trees. Meanwhile, there is no such concern for the graphs. But I told you that for the graphs you will have to take care of one more thing, and that is loops. So now let's see that why for the graphs you will have to take care of the loops and not for the trees. Okay, so for this graph, let's try to move in the DFS fashion, and we can start from iterating from any single node. So let's just say, for an example, we will start iterating from this node number 1. Now from this node number 1, who are the neighbors of node number 1? First neighbor is 8 and second neighbor is 2. We can pick any branch and keep on moving in that direction, depth first search manner. So say for an example, we start move in this direction. So first we visited node number 1, then we visit node number 2, then again we keep on repeating the same thing. So even for node number 2, it has two neighbors. First one is node number 3 and second is node number 4. So let's just say if we visit node number 3 as the neighbor, and next we visit node number 4. After visiting node number 4, again we have still two possibilities. Either we can visit node number 5 or we can visit node number 2, because both are neighbors of 2, so we still have two possibilities. Say after visiting this node from 4, we decide to move back on the node number 2. What would happen now is that from this 4 we would visit node number 2. Again from this node number 2 we would again visit node number 3. Again we would visit node number 4. Again we would visit node number 2. So see, we are stuck in a cycle, and because we are stuck in a cycle, we need to take care of that all the nodes that we have previously visited. If we don't know that what are the nodes we have already visited, and we keep on repeating this DFS coding technique on the graph, we could end up in a cycle, and this is going to keep on running infinitely. So this is a huge problem that we have to take care of, and this problem can be solved pretty easily by keeping track of either a visited array or a visited hash set. So you have two options to use. You can use a visited array or a hash set. Okay, I typically like to use hash set, but in many solutions you can also use an array as well. Both are going to incur the same kind of space complexity because you are using an additional data structure, but this is solving a very popular real life problem that is going to save you so much computational power. So say for an example, in this problem, we decide to initialize a visited hash set, that every single node that we have visited so far, we are going to mark it as visited before moving to the next element, and we would only move in the direction for the nodes that we have not visited. So applying this logic, again we start from this node number first. Node number first currently, okay, we say we have visited node number first. Okay, let's just mark it as visited. We move in the direction, we visit node number 2. Node number 2 has not been visited, so we can go in that direction. And again, let me plot the path on over here as well. So from 1 we move to node number 2. Again from node number 2 we have the possibility to move to node number 3. 3 has not been visited, we are going to mark 3 as visited. Okay, marking node number 3. Again going to the node number 4, marking node number 4 here, and node number 4 as visited. Now again from this node number 4 we have two possibilities. We can go to node number 5 or we can go back to node number 2. But when we try to go back to node number 2, we can clearly see that 2 has been visited. Since 2 has been visited, there is no point in going back to this node number 2, and the only direction we can go back to is going to be node number 5. So next we are going to visit node number 5. After visiting node number 5, we are going to go back to node number 6, and then we are going to go back to node number 7. And this is going to be like the one of the iteration or one of the paths we took starting from node number 1. Then we are going to do backtrack, and we are going to see that are there any other neighbors that we have missed that has not been visited, and that is not such a case for this one. So eventually after backing track or after doing like a backtrack, we would end up at node number 1. Again from this node number 1 we haven't visited this neighbor, so we will go in that direction. So we will go to node number 8. 8 has not been visited, we'll mark 8 as visited, and then 9 as visited. And then after visiting node number 7, we are going to visit node number 8 and node number 9. And this is going to be one of the DFS traversals starting from node number 1, where we eliminated the need for loops and we were able to iterate in a very smooth fashion in the DFS manner. So this is the whole logic, that why for trees you will have to use Inorder, preorder and postorder traversal. Meanwhile for the graphs you will have to take care of loops using either visited array or a visited hash set. You can pick and choose, but you have to remember that you will have to use it. Now let's see that what are different ways to iterate over in the depth first search. And there are two ways you can do it. You can do it recursively or you can do it iteratively. I'm going to show you both the ways before moving on to 3 solutions. Okay. Now, when it comes to DFS, there are actually 2 ways to implement DFS. First one is a recursive way using recursion, and second one is an iterative way. So first I'm going to show you that how does recursion works on a DFS and what is a typical flow of using recursion looks like for a tree and also for a graph. I'm going to show you both the examples. Now, before understanding and diving deep into the DFS, first you need to understand that how does a typical recursion works. Now, if you don't know what recursion is or how recursive functions behave, I encourage you to first go ahead and study recursion. Now, in this example, we have a binary tree, and for this binary tree, we will try to do the in-order traversal for this binary tree. Now, again, in-order traversal means left, node, and then right. This is the logic we are going to apply. So initially we are located at this first position. Now let me show you how the recursion is going to work for this tree using this root node example. Currently for this root node, we are going to apply the logic of left, node, and right. So first for this node, we will check that whether does it has left child or left subtree. Yes, it does has left subtree entirely. Now even for this left subtree, again we will have to apply the same logic of left, node, and right. So in this case, whatever we were implementing for this node or for this root node, now we are going to treat this node number 2 as our root node, stating that even for this entire subtree, if this was a tree on its own, again if we had to use in order traversal, we would use this logic on left, node, and right. And that way we are going to again for this root node try to see that does it has a left child, and yes, it does have a left child, that is node number 1, but this node number 1 does not have any children of its own. So this is going to be our terminating case where we will get out of the recursion because we cannot go anywhere further, and we can actually node this, we can actually treat this node as being like a process. So we are now at this position for this particular one, and this is how recursion is going to end for this portion at this particular node that we are done with it. So first node we are going to visit is going to be node number 1. Again, now we are going to do the backtrack, and after backtracking, even for this true, again we are going to apply the same logic that left we have already taken care of, but node we haven't taken care of. So now we will mark node because we visited all the left subchilds possible for this root node. But even for this root node, it still has a right subchild, and again if this right subchild, say for an example it had additional children, we would have again used this left node right logic. But since it does not have any additional children, we are going to treat this as a terminating case for recursion, and then the next node we are going to visit is going to be node 3. After visiting this, now we have taken care of all of these 3 nodes, and now we will go back to our root node. Again, we took care of the entire left subtree for this root node. So now we are going to mark 4 as visited as well, that we already took care of it, but we are yet to take care of the right side of the subtree. Again, rather than treating as a right subtree, we can treat this as a subtree or as a tree on its own, where we are applying the DFS. And again, for this node number 5, we are going to visit the left child or left subtree first. But since it does not have any left subtree, we are going to visit node number 5 itself, because we are visiting the node. After visiting node number 5, we will have to apply the same logic for the right subtree. And again, for the right subtree, we will have to visit node number 7 and node number 6. But again, from node number 7, we have a left child, which is node number 6. So we are going to visit node number 6 first before backtracking and visiting node number 7. And since 7 does not have any right child, we are able to go back. And now we have visited the entire tree on its own, and we are done with the recursion. Now, every single time, whenever we meet this condition, or whenever we have been able to mark the nodes, then we would call the we would backtrack and come back again until we are done with every single node inside the given tree. And every single time we are iterating over a new set of subtree, we are going to call our recursive function to implement the depth first search logic again. And this is how recursion would work on a tree. Let's see how the logic is going to change or remain the same for a graph structure as well. Now, even for a graph, again, the logic is going to remain same. We are going to have our recursive function. We are also going to have some terminating condition, that how when we define that the node has been completely visited and we can move forward. And again, in the graph, since we are applying the depth first search, we are going to keep on going in one branch before going in the other branch. So say for an example, in this graph, we start iterating from node number 3, because in the graph, we have the flexibility to go in any particular direction. Now, every single element in the graph has 2 items. It has a vertices and it has an edges. And depending on the vertices and edges combination, every single vertices has one or more than one neighbors. And we are going to visit every single neighbor. Now you already know that for a graph, we will have to take care of all the nodes we have visited. Otherwise, we would end up in a infinite loop. So we are going to have a visited hash set that is going to be much of a help to us. And using this visited hash set, we would be able to create a terminating condition for our recursive function. So let's just start iterating from node number 3. Now currently, first neighbor we are going to visit for node number 3 is going to be node number 6. Currently node number 6 is not visited. We are going to mark it as visited. Again, for node number 6, we are going to call the same recursive function that is going to call the neighbors of node number 6. Now, since node number 6 does not have any neighbors, the only neighbor it has is node number 3. But since node number 3 is where we started visiting, so let's just mark node number 3 as currently visiting as well. Okay, and now we are not going to go back to node number 3. So now we are going to mark node number 6 as visited. And after that, so this is going to be the terminating condition for a node to be considered as visited, that if we have taken care of every single neighbor for that particular node. So for node number 6, we are done. We are going to do our backtrack. And from node number 3, again, we are going to move to the next neighbors that is not node number 6. This is the key part, that is not node number 6, because we already mark it as visited. Again, for node number 3, let's just say we go in the direction of node number 4. So we mark node number 4 as visited. Now again, for the node number 4, we are going to apply the same logic and treat that as if the graph is starting its traversal from node number 4, because we are using our recursive function to call the next subsequent nodes. And for node number 4, okay, node number 3 we cannot go to, node number 5 we can. So again, mark 5 as visited. Again, from 5 go to node number 2. Again, from node 2 go to node number 1. So okay, 5 2 1, and again from node number 1 eventually we will come back to node number 3. And since there are no other nodes left, we are going to be done with every single element. Now again, for this case, now at node number 3's position, since we took care of every single neighbor of node number 3, we are going to consider node number 3 as done and the completion of DFS, because all the nodes that were present where we were able to visit them in a single go, and they are all mentioned in the visited hash set. If we want, we could have plotted on our graph as well, that after visiting node number 6 we would come back to node number 3, then we would go to 4 and then 5 and then 2 and then 1 and again come back to 3, but we are not going to do that. So this would be like a traversal path. It could also be possible that there is one more node number 7 over here, that is not connected with any edge, and there could be possible that there is also one more node number 7 and 8 that is not connected with any edge. So again, for this one, after traversing all of these values, still we are going to use recursion to go over these two nodes, and we are going to add them to our visited hash set, and then we are going to add them to our nodes that we have processed in some way, shape or the other form. And this is how recursion would work typically for graph and tree data structure. There is only one difference between recursion and iteration, but in order to understand, first we will have to understand that how does an iterative DFS works. So let's just see an example that how does a iterative DFS work. Now again, for the iterative procedure, I'm going to show an example for a tree and also for a graph, but I'm going to explain you very quickly. And the way iteration is going to work is that we are actually going to use stacks in order to implement our DFS function. Now we all know that what is the property of a stack. A simple property of a stack is that last in, first out. LIFO is the property, and that is what we are going to use at the most. We are going to create a stack, and inside the stack we are going to add our root node, and again we are doing the in order traversal. Okay, so left root node. So first we are going to add node number 1 over here. Okay, now after adding node number 1, we are going to see that does it has a left child. Yes, it does has left child. So who is the left child? Left child is node number 2. Again, for node number 2, does it has left child? Yes, it does, the node number 4. So we are going to mark node number 4 over here. Again, for node number 4, does it has a left child? No, because it does not have a left child, which means now we will have to process node number 4. So we are going to pop node number 4 out. After popping node number 4 out, currently the first node we are going to visit is going to be node number 4. Now after popping node number 4 out, again for node number 2, it does not have a left child that we haven't taken care of, so we are going to add the node number 2 next. Then again for node number 2, we haven't taken care of node number 5. So after popping node number 4 and 2, we are going to push node number 5. Again for node number 5, it does not have any more children, so we are again going to pop node number 5 next. After popping node number 5, we are going to backtrack. So we already took care of all of these three. Now we are at node number 1 position. We are going to pop node number 1 out because we are doing in order traversal. But after popping node number 1 out, it still has right child that we haven't taken care of. So we are going to push node number 3 again. And even for this node number 3, it does not have a left child. So we have been able to pop the node number 3 out. After popping node number 3 out, we still haven't taken care of the right child, right children or right subtree. So again for node, we are going to push node number 6. After pushing node number 6, we are going to check that whether node number 6 has any left child or not. Yes, it does. So because there is a left child, we will have to do a push operation. So we are going to push node number 7. Node number 7 does not have any more children, so that is a terminating case. So we are going to pop node number 7 out. And after popping node number 7, we would be able to pop node number 6, and then we would be done with our iteration. And this is how in order traversal is going to work using iterative method for depth first search. Basically we are using stack to keep track of the nodes that we already entered, and that is going to allow us to implement our backtrack much efficiently, and we would be able to solve this problem. Let's just do the same thing with a graph. Now this looks like a tree, but this is actually a graph because there exists a loop inside this. Typically trees does not have a loop, but graphs do. So that is why this is a graph. Again, let's just implement our iterative method. We are going to use stack. We are going to use the property of last in first out. And in our stack, again, we are also going to have a visited hash set because this is tree. So we will definitely need this. Say for an example, we start traversing from node number 2. We put node number 2 in the end. Now who are the neighbors of node number 2? So first neighbor is node number 4. Okay, now who are the neighbors of node number 4? None, because node number 4 does not have any neighbors that we have. And also we are going to mark 2 and 4 as visited. Now because there are no other nodes that are visited, that are not visited, and they are neighbors of 4, then we are going to do a pop operation. So first node we are going to pop out is going to be node number 4. After node number 4, we are again back at node number 2. Still it has neighbors that we haven't visited, so let's just say we visit node number 1. We mark 1 as visited, we add entry 1 over here. Again, 1 has neighbor 3 that we haven't visited, so 1 and 3 comes into the stack and visited has set. Again, 3 has node 6 that we haven't visited, so 6 comes here. Again, 6 has 7 that we haven't visited, so 7 also comes in the stack and also in the visited hash set. Now from 7, it does not have any more that we cannot visit, so now we are going to pop 7 out. So after 4, we can say that, okay, let's just say 7 has been popped out. Now again we are at this junction 6. For this junction 6, we haven't taken care of node number 5 and that hasn't been visited, so we are going to mark node number 5 over here as well. And from this node number 4, now every single neighbor of this node number 5 has been visited. So now we can simply do our pop operation. So first node number 5 is going to pop out, then node number 6 is going to pop out, and every single element is going to keep on popping out in the recursive fashion. So then 3, 1 and 2 are going to pop out, and this would be like one of the traversals. And everything we did not use recursion, we used the iterative method using stacks. So this is a key point to remember. Whenever you have to implement stack with an iteration, then whenever you have to use DFS iteratively, you must use stack, because this is the golden rule. And every single interviewer, if you show them recursive solution, they're going to ask you that, hey, can you do it iteratively? If you show them iterative solution, they are going to ask you to do it recursively. So it's good to know both the methods. And now let's just see some examples. So the first example we are going to see is going to be maximum depth of a binary tree. And this has been really popular problem amongst many top tier companies such as Apple, Google, Amazon, LinkedIn, Spotify, Microsoft, Facebook, Bloomberg, Yahoo, Uber. They have all asked this question. So this is a really popular question. And let's see the problem statement. Also, this is a very well liked problem and a LeetCode easy problem. Problem statement is quite simple. We are given the root of a binary tree and we need to return its maximum depth, which means suppose this is the example we are given. We know that the maximum depth for this one is going to be in this direction or in this direction. In either cases, the answer is going to be 3, because we are seeing 3 nodes in depth. So this is what we need to return. So the logic is going to be quite simple. We would be able to solve this problem using DFS quite easily. Now, since this is tree, we have 3 options to use: Inorder, preorder, or postorder traversal. We can use either one of them. I like using Inorder, so let me just show you the solution using Inorder. And for this problem, I'm going to show you the solution using iterative method. So I'm going to show you the solution with the stacks. So first, let me quickly initialize a stack that I'm going to use to iteratively traverse over this given tree. Also, we need to calculate the depth. So we are going to have a variable called depth, and I'm just marking it as DEP. And initially the value is going to be 1, because we are guaranteed to have a root node, and the root node by itself is going to have depth 1. So we already start with this one. Okay, now we are going to apply a simple logic that whenever we reach to a leaf node, whenever we move to the next element and we reach to the leaf node, this is the last element that we can visit in this path, nothing more than that. So up until this point, whenever we are going downwards, we are going to increase the count for our depth. But since this is DFS, we will have to do backtrack many times. And whenever we will have to do the backtrack, we are going to subtract the depth we have been able to find so far. And we are also going to have a variable called maximum depth that is going to allow us to capture the maximum depth we have been able to capture, because it could lie anywhere on the graph, so on the tree. So let's see the solution in action. Okay, first we already know depth is 1. Now from this portion we start the Inorder traversal. So we are going to do left node and right subtree logic. So we are going to go in the left direction since we went down, and again initially the first value is 1. Now next value we are putting in is going to be node number 2. Since we are going down in the depth, or we are adding value to the stack, in either case we are going down in the depth. So we are going to increment our depth. So currently now the depth is going to become 2. And so far the maximum depth we have been able to find is also going to be 2. Now again from this two stints, it does have a left node. We are going to again add entries to our stack. So we are going to increment the depth, and also the maximum depth we have been able to find so far is going to be value number 3. Again, now from this 4 we cannot go down any further, so now we will have to pop 4 out. The moment we pop 4 out, now we are going to go do a backtrack. So because we are doing a backtrack, we are going to subtract the value of the maximum depth we have been able to find to 2, not maximum depth but the depth we have been able to find to 2. Now the maximum depth is going to remain 3 because that is the maximum value we have found so far. Again from 2 we are going to add value number 5 inside our stack. Since we are adding value, we are going to increment the value of our depth to value number 3. The maximum depth is going to remain same. Again we are doing backtrack once and backtrack twice because we are going to get rid of these both of these elements. So we are now again at position number 1. Now position number 1 we are also being able to pop out because currently we are visiting the node, but it still does have right children that we haven't visited, and same with this one, the depth is going to change to 0 when we are at this portion. We already popped this one out as well. Now for this node number 3 we are going to put it in. So again depth is going to change. Now depth is going to be 1. Again for this 3 does not have any left children, so again we are going to process this node number 3, but we are going to keep depth as 1 because 3 is already located at depth 1, because 3 still has right children that we haven't visited. Now we are going to push to node number 6 in. So again depth is going to increase and depth is now going to be 3. And also from this then again we are going to have one more value 7 inside our graph. So we are going to have depth as 4. Since depth is maximum right now, we are going to increase the max depth as well. And after visiting this node number 7 we would be able to get rid of node number 7 and also node number 6. And now we have visited every single node inside the tree, so the maximum depth we have been able to find is going to be 4, and this is what we are going to return as the answer. So this is going to be the whole solution for this problem. And I know this was a LeetCode easy problem and very justifiably, and I like this problem because it opens your mind about the depth first search concepts and you would be able to solve it quite easily. Now let's see the coding solution for maximum depth of binary tree. So first of all, we are going to initialize a linked list called stack and also a linked list called depth. Then we are going to check for the edge case that if the given root is equal to null, we are going to return 0 immediately. If that is not the case, we are going to add the first value to our root, and we are also going to add that value to our depth linked list, stating that this is the node we are currently at. Now we are going to have two variables called depth and the current depth, and this is to keep track of the maximum depth we have been able to find so far. Now we are first of all going to iterate until the given stack is empty. Now first thing we are going to do is we are going to mark the root node as the last value we pull from the stack. Then we are going to add the current depth as the depth of poll last for this in this particular linked list. And then we are going to check that if the given root is not equal to null, in that case we are first going to calculate the depth, which is the maximum value we have been able to find, that whether the current depth is the maximum depth or not. And then we are going to add the left child, we are going to add the right child. Because we are adding two entries, we are going to add two more entries to our current depth at any given current location. So we are going to mark value by +1. And in the end, after this whole process is done, we only need to return this variable depth that contains the maximum depth we have been able to find. So let's try to run this code. And seems like our solution is working as expected. Let's submit this code. And our code runs decently efficiently in terms of space complexity and very efficiently in terms of space complexity. So I would be posting this in my GitHub repository. The description is mentioned in the comments, so you can check it out from there. The LeetCode problem we are going to solve is going to be path sum problem, and this is a very now the LeetCode problem we are going to solve is called path sum LeetCode problem, and this is a really popular problem asked at some of the top companies like Amazon, Microsoft, Google, Facebook, Bloomberg, Apple, Walmart, and Adobe. So I'm paying my utmost attention. So again, this is a LeetCode easy problem and also very well liked problem. If we see the problem statement, it's quite simple, that we are given the root of a binary tree and we are also given an integer called target sum. Now we need to return true if the tree has a root to leaf path that sums up to the target sum, which means suppose this is the input we are given and we are given the target sum is equal to 9. Then in this case we can see that if we do the sum of all these three elements, so this is the root node, this is the leaf node, and if we do sum of this path, then the sum is going to be 9. So in this case we are going to return true. But suppose in this case we were given the target to be, let's just say any arbitrary value like 11. In this case, since there is no path that sums up to value 11, we would have written false. So this is the whole ask of the problem, and the solution is quite simple. We would be able to solve this problem using depth first search method. Now suppose this is the input we are given and we need to check that whether the target sum is equal to 8 possible or not. So the solution is going to be quite simple. Let's just do Inorder traversal. Now we are going to do this recursively, iteratively, whatever you want to do. Let's just do iteratively. Okay, so we are going to use a stack. Now we are also going to use this function called sum of the path that we have been able to find so far, and initial value of the sum is going to be 0. The first value we pop inside the stack is going to be node number 1. Now again for this node number 1 we are going to increment the sum. Sum is going to be currently at 1. Now we are moving along this path 1 to 2. So again from 1 to 2, again we will have to add entry 2 over here. Again sum is going to be 2, so 1 to 2 is going to be value number 3. Now again from value number 3, from this position 2 we are going to move to this direction. So now we are going to add one more entry into our stack, and that is entry number 4. So now 3 and 4, the sum is going to be 7. Again it is not the target value of 8. Now currently we only need to consider the path sum from root to leaf. Now you notice that the sum that I have created so far, initially I was only doing the sum between these two entries. Even if that would have met the target value, we could not still consider it to be the path sum. So the question is that how do we know that the element is a leaf element? We only know it that if the element does not have a child. So the moment, even if we find the correct sum as the target sum, we will have to check that the last element we included, did it have any more children or not. If it does have children, then we would not consider it to be a successful scenario. I understand that my explanation makes sense to you. So now currently this target sum is 7. Now since at this 4 we cannot go down further, but we still have elements that we haven't visited. So say for an example, if that is the case, we are going to do a backtrack. So we are going to get rid of 4. The moment we do a pop operation from our stack, we will also have to reduce the sum as well. And now the current sum is going to be 4 at the sorry, not 4. The current sum is going to be 3 at the moment. Now at this sum 3, again from this 2, now this time we are doing a post order traversal. So we are doing left, right, and then node. Yeah, I know initially I said in order, but that was my mistake. We would be able to do post order in this one. And now we are going to visit the right node for again. Now this right node, the value is 5. Because we input 5, we are going to mark it as sum. So sum is going to be 3 plus 5. So sum is going to be 8. Now this sum matches this target value. So we will have to check that whether this 5 is a leaf node or not. And we can check it quite simply because this 5 does not have any more children of its own. We can mark this node 5 as leaf node, which means this sum equation makes sense and we would be able to return true in this case. Now using depth first search, you are able to solve this problem quite beautifully and quite efficiently. And if we see time complexity, the time complexity is directly in correlation with the number of nodes that are present. So we can mark it as big O of n, because for DFS we don't need to do anything else. In terms of space complexity, because we are using an additional stack, we will have to mark it as space complexity. But in the stack at any given position, we are going to have all the elements that are at max the depth of a binary tree. So it is going to be in big O of log n fashion, nothing, not the big O of n. And if you say that this is log n, your interviewer is going to be really impressed, because he thinks that you have really good knowledge of data structure and algorithm, which is true and which is awesome. Now let's see the coding solution for path sum problem. Now in the path sum problem, again we are going to move iteratively and we are going to initialize a node stack called linked list, and we are also going to initialize a linked list called sum stack that is going to keep track of the current sum we are at. Now initially we are going to add the root value to our node stack that we have created, and then we are going to add the value to our sum stack. So sum is going to be sum minus root value, because we are adding the value inside our root node. Now we are going to have a tree node to iterate over the different tree nodes, and we are also going to have keep track of the current sum. Now again, for the iterative method, the method is quite simple, that until the given stack is not empty, we are going to keep running inside the loop. Now in the loop, first thing we are going to do is we are going to poll the last element that is present inside the stack. Because we poll the element, and we are also going to mark the current sum to whatever the sum we have been able to find for the last poll stack element. Now we are going to run a condition that if the given right node is equal to null and left node is equal to null, which means that both the nodes are at the correct position and current sum is equal to 0, which means that the current sum is the target sum, then in that case we are going to return true. If that is not the case, and if right node is not equal to null, we are going to deep dive into the right node and we are going to add the current sum we are at. If that is not the case, and if it has a left node, again we are going to repeat the same thing, and we are going to subtract the sum from the current sum, because current sum is the total number of sum that we need to return. And in the end, if we haven't returned true but in this loop, which means that the target sum is not being able to meet up between the root node and the leaf node, so in that case we are going to return false in the end. Now let's try to run this code. Okay, seems like our solution is working as expected. Let's submit this code, and our code runs decently efficiently in terms of time and space complexity. Again, I'm going to post the solution of this code in my GitHub, so you would be able to check it from there. Now let's see a really popular LeetCode problem called course schedule, and this is a LeetCode problem 207. This has to be one of the most asked graph and tree kind of a problem. It has been asked in all kinds of companies such as Google, Amazon, TikTok, Microsoft, Facebook, Apple, Uber, ByteDance, and then Bloomberg, Snapchat, and bunch of different more. So this problem has been really popular. Let's see the problem statement. Basically, this is a LeetCode medium problem, very well like problem. Now in the problem statement, we are given an integer value called number of courses. Suppose we are given the integer value of number of courses is equal to 5, which means that we are given that there are 5 courses, 0, 1, 2, 3, 4. These are going to be 5 different courses that we will have to schedule for. Now we are also given one more thing, and that is that we are given the prerequisites for any single course. And this prerequisites is a really common thing, because even in real life we all have been to universities, and if you want to do, say for an example, comp 202 course, then it must have a prerequisite of comp 101, that if you haven't completed comp 101 you cannot get admitted into comp 202. So this is just an example of what a prerequisite is. Now in this case, we are given an array of prerequisite where every single tuple is a value such as A and B, which means that in order to complete course B, we must first have taken course A. So suppose we are given that in this case, we are given 5 courses, 0, 1, 2, 3, 4, 5. And if we are given a value such as like 0, 1, which means we can determine that in order to complete course 0, we must have completed course 1 first before moving forward. So using this logic, we would be able to use this as to create an edge between any two nodes, and we are going to treat number of courses as nodes. So now we have both the values we needed. We have a node and we have an edge, which means we can create a graph based on the given input. So suppose again we are given 5 different courses, and say these are the dependencies, right? That 0, 1, 2, and then 3, and then 4. So these are the 5 courses that we are given, and these are all the dependencies we are given. So quick question, are we able to complete all the courses in this problem? Of course we can. Why? Because first we are going to complete course 0. In order to complete course 0, we will have to complete course 1. In order to complete course 1, we will have to complete course 2. Course 2 we can complete because it does not has any prerequisites. So after completing course 2, we would be able to complete course 1, and then we would be able to complete course 0, which means we would be able to solve our this dependency quite easily. Same goes for this one, that we can complete course 4 because there are no prerequisites needed for course 4, and then we can complete course number 3. So in this case we can return true because all the courses can be scheduled. But suppose we are given a scenario like this, that again we are given the same set of conditions, but we are just given a tricky scenario where in order to complete this course number 2, say we will have to complete this course number 0. In this case, now will we be able to schedule all the courses or take all the courses? The answer is no. Why? Because these courses we can still complete by completing course number 4 and course number 3. But now in order to complete course number 0, we will have to complete course number 1. In order to complete course number 1, we will have to complete course number 2. In order to complete course number 2, we will have to complete course number 0. So we are running inside a cycle and we would never be able to get out of it. And that is the whole crux of the problem. So the problem simply becomes that we take the number of courses that we are given, we treat them as nodes, the prerequisites, we treat them as an edge, and then we create a graph. After creating a graph, all we need to do is run a DFS. We can do it recursively, iteratively, it's up to us. And after using this DFS, all we need to do is to check that whether there exists a cycle or not. And how can we check that there exists a cycle or not? Using visited array or visited hash set. And this is why a lot of companies love asking this question, because see how many different topics it covers in a single problem. That is a real life use case that is pretty popular in many universities. So that is why a lot of companies like to ask this kind of question. Let me quickly show you the solution, and I urge you to think hard and deep on this problem and try to solve it on your own. But I'm just going to show you a quick implementation of the solution. So suppose, again, let me just go back to my previous scenario. Suppose these are all the prerequisites and graphs we are given. So now we will try to see that whether there exists a cycle or not, which means we are going to run a DFS simply. Now this is a directed graph, which means if there exists an edge between node 0 to 1, it is not necessary that there has to exist an edge between 1 to 0 as well. Now we are going to first initialize our visited hash set. We are also doing this iteratively, so we are going to initialize our stack for our DFS. We are opening both the buckets. Suppose we start iterating from 0. Now from node number 0, in order to complete node number 0, we will have to complete node number 1. So first let's just mark node number 0 over here, and we are going to say that okay, node number 1 is a neighbor of node number 0. So since 0 has a neighbor currently, okay, we mark 0 as visited. Now 0 has a neighbor 1, so we are going to add 1 to our stack. Again 1 has a neighbor 2, so we are going to add 2 to our stack, and at the same time we are going to mark them as visited. Now 2 does not have any neighbors, which means we can pop 2 out. After popping 2 out, we would be able to pop 1 out. After popping 1 out, we would be able to pop 0 out, which means we took care of this entire path and we found no issues, and currently we have been able to visit this node 0, 1 and 2 in our visited hash set. But we know that we are given 5 courses, and currently so far we have only visited 3 courses. So since there are 2 more courses that we have to visit, so let's just start by visiting course number 4. Now course number 4 does not have any neighbors, which means we won't be able to do much with it. But for course number 3, it does have neighbors. So currently they just start with no course number 3. So course number 3 currently has a, and we are going to mark 3 as visited. 3 has a neighbor 4. We are going to mark 4 as visited. And in the end, since we visited all 5 nodes, we found no issues, which means we can return true that we did not find any cycles. So by implementing the graph function, we can say that all the courses can be scheduled. Now suppose there exists a cycle. So suppose even in this case, from this 3 to 4, there was a cycle. So again 4 has a value that points to 3. So again 4 is calling a neighbor 3. So we will try to put 4 into the stack, and we would try to add entry number 3 over here. But we would say, hey, 3 has already been visited. So since visited node cannot be visited again, so we are going to say that cycle exists, and we would be able to return false in this case. And this is the whole solution. If we see time complexity is going to be big O of v plus e, where v is the number of vertices, e is the number of edges. So v plus e is pretty standard for any graph kind of a problem. Space complexity is going to be directly correlated with, because of these 2 items. So it is going to be big O of v, or big O of number of vertices. And this is a really popular problem, and it has been liked by all people all across world. So that is why I ask you to solve this problem on your own, because it is going to be really helpful for your next interview. Let's see the coding solution for course schedule problem. Now in the course schedule problem, we are not given by default the structure that looks like a graph. So first of all, we are going to create a hash map where we are going to keep an integer as a key and the list of integers as the value, and we are going to name it as course dictionary. Now we are first of all going to build up a graph structure that we will be able to iterate, where depending on any given course, we would have its dependencies listed inside the hash map, and the hash map is going to allow us iteratively allow us to do all the procedure quite smoothly, because we would be able to fetch all the data in big O of one time. Now after creating the graph like structure, we are going to have two variables. First one is called checked, so this is going to be our visited array, and second one is the path. This is the number of courses that are currently present in the path or not. Now we are going to run a for loop, and in a for loop we are going to go over every single course until we reach out of them, and we are going to check that whether from the current course are we able to create a cycle or not, and we are going to give as an input all the checked courses that we have gone through and all the paths that we have gone through, and this is going to be a helper method. So let's see the is cyclic helper method. Now in this helper method, first of all, we are going to get our hash maps, all the graph and all the data. First thing we are going to do is to check that whether the given node, if that has been checked or not. If that is checked, which means that there is no cycle and we can return false. If we are also going to check that are we going through the previously visited node. If that is the case, which means we identified a cycle, and we are going to return true immediately. Now if both are not the cases, we are going to check that if the current course dictionary contains the course that we are currently at, which means there is no loop, so we are going to return false. If that is not the case, we are going to mark that the current course we are at that has already been in our path, and we are going to have a boolean variable set to false. Now again we are going to run a for loop for every single child of the current course, and we are going to again recursively call this method again and again and again. And at any moment we identify that this return variable is not false, we are going to is false, we are going, and at any moment we identify that this return variable is true, that means we are going to break out of the loop, and we are going to mark that the current path is mentioned as false, and we are going to say that the current course we have already returned as true. In the end, we are going to return this ret boolean variable that we set up. Now let's try to run this code. Okay, solution is working as expected. Let's submit this code, and our code runs pretty efficiently compared to in terms of space and time complexity. And I would be posting the solution of this code in my GitHub, and the description of the GitHub link is present in the description of this video, so you can check it out from there.